Hi, this is Steve, K8BZ. We're going to take a look today at some noise that's been very loud and disruptive for the past couple of weeks. It's been on and off, but here lately it's been on almost 24/7. It's very hard to copy any signals through the noise. It's so loud on HF. I can also hear it on VHF, even though in FM mode it's not quite as disruptive. But we're going to take a look at some ways to identify the noise and see about getting it corrected. We pretty much eliminated that it's anything with the rig, especially because we can hear it on HF and VHF on two different radios. So it can't be the radio that's the problem, an individual radio. Now, it could be feeding through the commercial power. It could be something in the house here that's generating electrical noise. But we've also eliminated that by shutting off the electrical service to the house via the main at the circuit breaker, and we can still hear the noise in the mobile radio in the car on HF and VHF. So pretty much it's been traced down to something that's being radiated in the area that's being picked up by the antenna and delivered to the radio. And because it stops abruptly and begins abruptly when it begins and ends, atmospheric conditions don't do that. So that leaves us with some electrical source of interference in the area. I'm going to turn the volume up just a little so you can hear it. That noise right now is at an S8 on the S meter. Now I have both preamps turned on just so I can get a good indication on the spectrum scope. We're on 12 meters, and you can see those spikes at the bottom of the spectrum scope. I'm gonna zoom in on those just a little bit so you can see them clearly, and then we'll pan back out where we can see the entire display. Something that's helpful to note here is that the static noise and the spikes are very evenly spaced. That's a very even interval between the static crashes that we hear in the receiver. As you can see on the band scope, those spikes are pretty uniformly spaced across the band. Now we get the same noise on the other bands, but I won't switch and show you. It varies a little bit in strength from band to band, but it's across the entire HF spectrum. I'm getting the best indication here on 12 meters, so I'm just going to leave it on 12 meters for now. Now going back to the display where we can see the entire display, including the S meter, we're going to try and see where this noise is coming from, whether it is coming from all directions or whether it's coming from one specific direction. I'm going to turn the volume up just a little so we can hear the noise, and then I'm going to rotate the beam antenna to see if the noise is louder from one direction than another. As you can see, we're going to look at the amplitude of the spikes and the S meter. You can see the S meter is dropping as I rotate to the west. Now the antenna is pointed about northwest. It's down to an S0. The spikes are almost gone. Now I'm going to pan back to the east. You can see the S meter rising. That's about due north. Now we're northeast. Now we're at about an S8. It's continuing east, and it's dropping just a little. It's still staying quite high, but it is dropping just a little. We're down to southeast right now. Southeast on the antenna. Now I'm going back to the north again. I'm going to try and see where we get the strongest reading. Back to an S8, peaking slightly above S8, and we're back to northeast. Northeast of my location is where we're getting the strongest indication, and as I continue further north, the S meter drops down. Now I'm due north and it's dropped down again. If I continue, it'll drop down again to near S0. So the strongest reception of this noise is to the northeast. So there's something northeast of here that's generating a lot of static. and basically making HF near useless here, and it's been that way for almost 2 weeks. Okay, now we're looking at 2 meters. We're going to do the same directional test on 2 meters by rotating the beam. Same test we did on 12 meters, and compare the results, and hopefully the results here on the 2 meter test will confirm the results on 12 meters. I have the volume turned down now. The antenna is pointed northeast. It's the same direction we got the strongest indication on 12 meters. The antenna is pointed northeast. Turn the volume up a little. Actually, before I do that, I want to mention you have to do this in single sideband mode. If you have this problem and you're going to check 2 meters, don't do it in FM. You're not going to get, you're not going to hear the static. You might see the S meter indication, and the S meter indication might be so subtle that you won't notice. But the arcs create an amplitude modulated source of RF. It's not frequency modulated, so you're not going to hear it in FM mode like you hear it in single sideband. You could also listen in AM mode, but I found the single sideband kind of gives you the best audible indication. So we'll turn the volume up. You see the S meter now is about at S6. I'm going to rotate the antenna to the north. And you see the S meter start to decline, and the noise almost totally disappears. I'm just a little bit west of north right now. I'm going to go back to the east. We're approaching northeast, and you see the S meter reading is climbing, so is the sound of the static. And now we're continuing east, and you see the S meter reading decline, and the noise also decline. So I'm going back to northeast. So we see that the test here on 2 meters confirms the results that we found on 12 meters. Now one way that will help convince Consumers Power Company that it really is an arc in the commercial power system is if we can determine the frequency of the noise, the frequency of the static, or the frequency of the sparks or arcs that are occurring. A good way to do that is by using an oscilloscope. We can't really determine the frequency of it on the spectrum scope on the radio. We can see that they're pretty even intervals, but we can't really determine the frequency. So what I've done is I've run a cable from the headphone jack on the radio across the room to the test bench and to the input of an oscilloscope. And you can see those large spikes on the display of the oscilloscope. Now what we have to do is set the horizontal sweep frequency on the scope to get a good indication to help us get an accurate reading on the scope. I'll show you what I mean by that. I'm gonna increase the sweep frequency, and as I do, those pulses get further apart, but it gets a little harder to read. We want to see those spikes as plain as we can. Now I'm back down to where it was originally set. That's at 5 milliseconds per division. I'll explain that in a minute. If I slow the sweep frequency down a little more, we can still see the spikes there pretty good. But for me, 5 milliseconds per division seems to work pretty well. Now that we've got that sweep frequency set, you can adjust the volume. You can do a couple of things. You can adjust the horizontal gain. You can adjust the vertical gain of the oscilloscope to get the height that you want on those static spikes. That seems to be a good spot for me. You can also adjust the volume on the radio. I'm going to go back across the room to the radio and adjust the volume. If I turn the volume all the way down, it just flatlines. As I increase the volume, you see those spikes come up. So we want to get a good display where we can see the spikes. So we can see them pretty good there. So I'm going to zoom in now just on the display so we can get a good look at that. Okay, had a little bit of difficulty getting it to focus just on the display, but finally got it. Now we're going to adjust the position on the display I'm going to try to get one of those spikes to where it begins right at the center vertical division right here. Now it's kind of a judgment call. You can see it flashes a little more in the camera view than it does when you're looking at it in person, but you can see I've adjusted it so the beginning of a spike is occurring on this first vertical display. Now we have the horizontal oscillator set, like I mentioned, at 5 milliseconds per division. The divisions are these large divisions. So from here to here, that represents 5 milliseconds in time. Now those divisions are further divided into 5 divisions apiece with little lines on the graph on the display. So we can see what the time interval is in between these arcs that we're receiving. So from here is 5, and then about 3 more small divisions to the beginning of the next arc. So it's about 8 milliseconds from the beginning of one spark to the beginning of the next spark or arc that's causing this static. Kind of keep that in the back of your mind. 8 milliseconds from beginning of one to the beginning of the next. Using that, we can determine the frequency of the static. One thing that's helpful to understand is that static from a public electrical utility usually occurs at a specific frequency. And if the static you're receiving matches the frequency of typically the frequency of the arcs that occur in some faulty component in the commercial electrical system, then you've gone a long way toward convincing consumers that it's their issue and not having them continually ask you to check this and check that in your house before they'll get involved. Now you might think because commercial power is 60 cycle that that's the frequency of the arc, but that's not the case, and we'll explain here. If this represents 0 volts, what we're going to do is take a look at one cycle of commercial power. There's the positive half of the cycle, the negative half of the cycle, and we're back to 0. So here we're at 0 degrees, here we're at 180 degrees halfway through the cycle, 360 degrees here. This would be the 90 degree point. This would be the 270 degrees point in the cycle. Now, if an arc is going to occur in a defective component in the commercial power system, it's not going to occur here, or here, or here. Those are all at 0 volts or at ground potential, and that's not going to cause an arc. They're going to arc at the high voltage points in the cycle. And basically there's two. There's a high voltage point here on the positive half of the cycle, and there's another high voltage point here on the negative half of the cycle. Both of those are at their maximum potential as compared to ground in one cycle of alternating current. So there's 2 arcs per cycle. If it's 60 cycle AC and there's 2 arcs per cycle, then there's going to be 120 arcs per cycle of alternating current. In other words, the frequency of the arc is going to be 120 hertz. Now, if we can match that to the frequency of the interference we're receiving, then that's a good indication that it's from a commercial power source. Okay, as we know, commercial power is 60 cycles or 60 hertz. The arcs are going to occur twice per cycle. That's going to make 120 hertz the frequency of the arcs that occur in the commercial power system. We also determined from our measurement on the oscilloscope that the static is occurring every 8 milliseconds. That's 0.008 seconds. So how do we determine the frequency of the static that we're receiving? Well, how many times does 0.008 go into 1 second? It occurs every 8 milliseconds, so how many 8 millisecond intervals are there in 1 second? So we take 1 second, divide it by 0.008, and that is 125 arcs or hertz per second. Now that's very close to 120 cycles that we would experience in a commercial power system. There's a little bit of leeway there for measurement error on the oscilloscope and a little bit of leeway for the actual frequency of the commercial power being generated, but that is very, very close and a very good indicator that the fingerprints of this are showing that it's from commercial power. So the problem now is, which pole is it? We already determined it's coming from the northeast, from my location, from checking on the antenna where the strongest signal is. So now we'll take the foxhunt antenna, go out to the car, we'll go on 2 meters and go pole to pole to see which one is giving us the strongest source of noise to the northeast from here. There's only about 3 or 4 poles that could be a suspect, so we're going to go out and check each of the poles and see which one is the strongest source of the noise. Now, this noise does travel down the transmission line, so we're going to hear the noise quite a distance either side of the defective equipment, but we should get the strongest indication from the pole where the arc is occurring. Now, these arcs are usually very small. It isn't something typically that you can see. Now, that isn't quite the case on this, as we'll see, but we can identify the pole, and then when we talk to consumers, we can tell them, I know where the pole is, here's where it is, here's how I found it, and you can get somebody out to verify it on their side very quickly, and hopefully get it addressed sooner rather than later. If and when you get through to the right person at Consumers Energy, they will send you this packet of information. There's a cover letter, basically, that says, we received your inquiry about radio/television interference problem which you are experiencing. And basically what they're saying is that most of the time when they receive those complaints, the source of the interference is not coming from something that's their responsibility. It's coming from the homeowner's equipment, dimmer switches, doorbell transformers, other electrical equipment, computer equipment, and for them to send out their specialists to try to track this down when it's not something that's their responsibility is kind of costly for them, and you can't blame them. They want the homeowners to do all they can to try to eliminate other sources of the problem before they involve their people. So they send another letter, informational letter here that tells all about the other sources of electrical interference and how to test as best you can to eliminate those as possibilities. And then they send this form to fill out and complete and mail back to them. Then after that, the specialist will get in touch with you and see what they can do. Now then, they still have to locate the source of the problem. With commercial power, usually the problem is at a utility pole. That's where all the connections are. It's usually not on the lines between the poles unless there's a tree limb or something that fell on the line, and usually those just burn off and fall off on their own. So it's usually at a utility pole where there are multiple connections, splices, transformers, cutoff switches, insulators. Those are all sources of potential gaps, very tiny gaps sometimes, that create a small spark that's very hard to see, but it can be detected with some special equipment. So if you can bypass all of this form process and 2 ways in the mail and being in someone's inbox, waiting for them to get to it and get back with you, you can save some time in getting some of these issues resolved. So the issue here is, if the hams can locate the utility pole that's causing the problem and notify consumers, that kind of puts it on the fast track to get resolved. Okay, basically we had toward three telephone poles where we were getting the biggest static signal. So of course I'm going to go to the one in the middle, which is where we are right now, and I'm just going to sweep past it. I already found a spot here with the polarity that will give us the best indication. Going about 45 degrees either side of the pole. Right now I'm pointed directly at it. About 45 degrees the other way to the south. Directly at the pole. 45 45 degrees the other way, written all in the antenna pattern. So this is probably our prime suspect, so we're going to take a real good close look at the pole. Okay, here is our suspect utility pole. This is some 7 to 10 days after it was first identified as the source of the static. I didn't take any videos of it at that time because there wasn't anything to see but a telephone pole, but over this past 10 days there is visible evidence, quite stark visible evidence of the arc, and consumers was aware of this. Well, they became aware of it after I told them. We did bypass that paperwork process. When the guy came down and verified with me that this was the source of the problem, he marked the pole. The pole is going to have to be replaced. They have to wait for Miss Dig to come out and identify all of the other buried lines around the pole, because this pole is providing underground electrical service to the neighbor's house. But we'll take a look at what's going on here from a couple of other views. Sometimes the source of the problem can be the insulators. Those insulators aren't all one piece. Those look like they may be two section insulators. There's sometimes 3. There are metallic parts in the insulators, and sometimes there's a gap there that the insulator becomes compromised. In that case, that's not what's going on here. This is the transformer. The discoloration on the transformer has nothing to do with the defect. That's apparently just a poor paint job. The transformers usually aren't the issue. If there's a short in the transformer, usually the transformer self-destructs in quite a visible light display if it happens after dark. That actually happened to me once. The insulators on the top sometimes can be an issue. If the insulators are compromised, there can be something in there that arcs. Now this is the knife switch. That's the power cutoff switch. The lines are above that. The transformer is just below it. There's a knife switch there where the utility workers can reach up with an insulated pole and open that switch to cut off electricity to the house before it reaches the transformer. That's where our issue is. You can't see it very well from this angle, but we'll get another angle. You can see the dark charring around the pole there. That wasn't there 10 days ago when this pole was first identified, but 10 days to 2 weeks over time, that arcing in there has really damaged the utility pole, and we'll show that. Okay, from this angle you can see the cross arm, the top of the transformer, and the knife switch. Notice the black charring there. The knife switch has 2 bolts that hold the insulator and the switch. Those bolts go right through the pole, through holes they drill through the pole, and they tighten those bolts. The arcing has been occurring at those bolts at the utility pole. You can see the upper bolt still has wood on either side of the pole. The lower one, the lower bolt is burnt better than halfway through the pole. Now this didn't happen in one event. This has been slowly going on and is still going on. Because I can still hear the arcing at 120 hertz, as I explained earlier. 120 hertz as verified on the scope at 125 hertz, and that is slowly burning its way through that utility pole, and it's burned better than halfway through. Okay, I'm going to get a couple other quick angles here just to get a good look at it. If you notice that insulator kind of on a diagonal there, that's where the knife switch is. And you see that black line on the insulator. That most definitely, most likely, I won't say definitely, but is very likely is a crack in that insulator, and has compromised the insulator, allowing some current to flow through to the supporting hardware, which when the pole is wet, shorts it to ground and heats it up very hot and burns the pole in half. There's not much holding that pole, that upper part of the pole up right now. Just about maybe 20% of the pole, if that much, is left, and we'll take a look at it from the other side also. Here's a view from the other side. You can see the that insulator, the black line on the insulator where the insulator is damaged. Also, if we look at the pole a little closer, you can see where the pole is cracked. What remains of the wood that's intact here is cracked. So A good windstorm and a little bit of stress on that is probably going to snap that portion of the pole right in two, and everything's just going to be hanging by the wires. I sent pictures of this to consumers, and that got the guy down here that day to look at the problem, and got things rolling. Hopefully they'll have this fixed so I can get back on the air, because I may have a federal civil rights violation here, because this is definitely interfering with my pursuit of happiness, because I can't get on the air on HF. I've made a few contacts in between brief periods of time where this static isn't present, but S5 to S9 static does not work well when you're chasing DX that has an S1 or 2 signal strength. Get one more view and that should wrap it up. Trying to find a view here that shows just how far gone this pole is. And that may be about the best view I can get. But that's the situation. Pretty much that pole is toast. Thanks for watching.